webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for attending today's webinar, Best Practices for Creating Strong Bonds Using UV, LED Curing, and Plasma Treatment. Please note that this webinar is being recorded, and you will be able to access both the recording and presentation slides once they are available online, which should be within 24 hours. If you have any questions during the webinar, please use the GoToWebinar question tool. We'll reserve time at the end of the webinar to answer as many questions as we can. Today we are fortunate to have two very knowledgeable presenters with us. As Director of Product Management of Excelitas, Mike Kay works closely with customers to design and develop both lamp and LED UV curing solutions for a variety of industrial applications. Mike's extensive industry experience makes him a sought-after speaker on the topic of repeatable UV curing processes. As Vice President of Sales for Enercon Industries, Ryan Schilke leads a team of knowledgeable surface treating application specialists. His passion for innovation and customer success is a driving force behind Enercon's plasma and flame surface treating solutions. Some of the topics that we'll cover today include emerging applications for cured inks, coatings, and adhesives, how plasma and flame pre-treatment promotes surface adhesion to enable stronger bonds, how to select the right pre-treatment technology for your application, some of the benefits of integrating a UV LED curing process, how to determine the best curing technology for your application, the latest advancements in both plasma treaters and curing systems, and we'll again conclude with a question and answer session. First, a brief background on Enercon. Enercon was established in 1974, and today it is an international company with operations in the USA, United Kingdom, and India. This is along with a sales and service network that supports their customers around the globe. Enercon is recognized as an innovator of plasma, flame, and corona treating technologies. And with that, I would like to turn it over to Mike to talk a little bit about Excelitas and UV curing.
Thanks very much, Mark. Just a quick overview, Excelitas Technologies. We are the OmniCure UV curing brand. We have been developing UV curing systems since about 1984. Previously, the company was Lumen Dynamics. We were acquired by Excelitas back in November of 2013. This now gives us a broad network with locations globally. We now have the support of over 5,000 employees. And as the OmniCure UV curing systems, we have about 30,000 UV curing systems globally. That's what is currently in use now by manufacturers. So we have a pretty good history and understanding of a number of different UV curing applications. And as you'll see in the next slide, we have both lamp and LED curing systems. So we have a long history in lamp. More recently in LED, there's certainly been a lot of interest from people in looking at LED technology. And we have a lot of experience with our customers as they transition their process from curing with lamp-based technology to LED. You'll see here, this gives you an idea of our family of products. We have both spot and area curing systems, again, both lamp and LED. And some of the things we like to make sure is included in all of our systems because we know the importance of it for the curing process. Things like control allows you to adjust the irradiance of the UV in your curing process. Wavelength selection allows you to choose the wavelengths that are required. Radiometry for measuring the output. We understand certainly one of the areas where had some success in is with medical device manufacturing and other applications where the repeat build a number of features into our products to make sure that they get the highest repeatability, and of course support. We do have application support globally, and we are able to take our standard products that you see here, the spot curing at the top, the AC area curing at the bottom, and do custom requests for people as needed. And with that, we'll look at some of the emerging applications for inks, coatings, and adhesives. And if we go to the next slide, we can see an example of a number of different applications that are currently done with LED. As I mentioned, A lot of these are applications that have been going on for a number of years using lamp-based technology, and now there's a lot of interest in transitioning these to using LED. I've tried to separate them by applications that have been traditionally spot curing, others that are area curing, and you can see in the middle there's some that you could use either spot or area curing. But I think what you'll notice is there's a mix of a lot of different types of applications, different industries. There's medical applications, you'll see electronics, certainly some of the areas we're seeing emerging, things like OLED displays, touch panels, and also some different industrial ones, things like solar panels, fiber coatings. So there's a number of different applications in all areas that are looking to transition to LED, and so we'll try to talk about some of the best practices, things to look for, and certainly some of the benefits of using LED. I will go into a couple in more detail. On the next slide, you'll see a couple of areas we've really seen some interest. If we go to the next slide.
Let's see. Mike, we've advanced it, but it's not appearing yet for some reason. It should be just a second.
Detail is things like lower temperature curing, which is ideal for a number of the plastics that are used on the different applications such as catheters, insulin pens, syringes. So this is a very nice fit, but we have seen a reluctance in the medical device to move to LED up until recently. And there's different reasons why. With medical device, there's a lot of regulatory process involved. And so moving away from traditional lamp has been difficult, but we're seeing that as one of the emerging areas for LED. And another one of the big areas for LED technology is in printing. And printing, there's some real benefits to LED technology, again, from temperature-wise. But here you're also looking at reduced cost of maintenance. And one of the reasons we've been able to see the LED come into play in printing is the increased output power that LED systems now have. You're now seeing systems 12, 16, even 20 watts per square centimeter of irradiance, which now allows the LEDs to really meet the speed demands that are required in the printing. But really one of the areas that is also caught up on both the medical and the printing is the compatibility of the formulations of both the adhesives and the inks to work with the LED. And that's one of the real important areas, is that it's important that the material you're curing works well with the light-based technology that's being used, and that we're seeing that now on both medical device and printing, and it's a very nice fit for both of these. Certainly with plastics, there can be some difficulty in getting adhesion, and so this is why I think one of the areas that ties in really well is the ability to use some form of pre-treatment that is very helpful with difficult plastics such as polypropylene or polyethylene. And with that, I'm going to pass it on to Ryan to maybe talk a little bit more about that.
Great, thanks, Mike. Yeah, and one of the great similarities between our companies is that we do tend to work on many of the same projects together. The applications that typically apply for UV curing tie in very nicely with our plasma treating solutions. So as we get started, we're going to talk a little bit about just what the adhesion dynamics are that we're dealing with, both with plasma treatment and ultimately with UV curing. So you have to take a number of pieces into consideration. Mike mentioned polypropylene, polyethylene. That is a great example. That material is one of the first things that we're going to look at in understanding what sort of adhesion challenges we might have with a product. Another component is going to be what sort of additive load is in the molded part that you're looking to treat. Those additives do tend to migrate to the surface and do have an impact. We'll talk a little bit more about that here in a couple of minutes. As it pertains to the surface, we're going to look at the chemistry and roughness of those and the adhesive chemistry. So what we really want to make sure we understand is what does the surface chemistry consist of, as well as what is that adhesive chemistry as well. So that could be either a traditional adhesive, it could be a coating, it could be an ink. And ultimately, you'll look at what sort of stress that bond is going to go through the life of the component that you're manufacturing. So when we talk about adhesion, we're really looking at two components. We're looking at adhesion, which generally is what we're looking for, and that is the property of unlike molecules to attract. But we also have to look at the force of cohesion, and that's the force of the property where liquid molecules like to remain together. And ultimately what we're talking about is wettability. And we'll dive into this a little bit more as we go through. So some of the challenges that you see with any surface is many plastic products inherently have a low surface energy. And a number of components come into play here. One, there may be contamination on the surface. That could be foreign material that's accumulated on the product after it was manufactured. It could be mold release that may be left over. Any number of components can contaminate the surface and ultimately lead to challenges with applying an adhesive, a coating, or an ink. I mentioned additives. So additives will migrate to the surface over time. This is going to vary based on material. It's going to vary based on the additives that are involved, but it is something that you definitely need to pay attention to, and one of the critical factors that we find in people having challenges with their adhesion. Additionally, plastics inherently have a limited number of bonding sites, areas for that adhesive, ink, or coating to grab onto. All of these things contribute to a surface that is hydrophobic, or one that wants to take that force of cohesion and keep those molecules together and not create a strong bond. So what sort of options do you have? How can you prep the surface? Mike alluded to this, that there were options for preparation. One of those would be to use a liquid or chemical primer. Very common process, maybe a wipe of some sort put across the process. And this can be a very effective means of prepping a surface. The challenge with it is it tends to be a little more costly. You often have a human being involved in actually wiping the part. In many cases, there can be hazardous material, so you've got to look at what cleanup is required, how you're going to dispose of those products, and just the health impacts of those chemical primers being used. Another way, some applications will use a mechanical preparation. This could be using a sandpaper to roughen a surface, maybe skiving a surface as well. And again, can be a very effective process, but it does create challenges. We talked about wanting to clean the surface. Anytime there's going to be a mechanical prep, there's going to be resulting materials that are left on the surface, which again is something that you want to avoid in getting the strongest bond. There are parts involved that maybe have to be replaced over time. Again, now is the best solution, particularly when you look at composites. If you then do use some sort of mechanical preparation, you have to be very careful not to go in and hit the carbon fiber strands or the fiber strands that are used in those products. As you start to hit those and damage those, you do decrease the strength of that part pretty significantly. Vacuum plasma is another option. That's going to be where you load a tray of your parts into a chamber. It runs for a set period of time. It's a very effective means of treating an entire part, but again, in any standard production environment where you need things flowing through the system consistently, this tends to be a very time-consuming process. Atmospheric plasma and flame plasma systems are a bit different here. We do affect the surface. There are no chemicals involved from a health, from an environment perspective. They are very safe systems. They're able to be used in a continuous environment, and they are very economical solutions as well. So let's dive in a little bit more deeply on how atmospheric plasma treatment systems help promote adhesion. So we often get the question, what is plasma? What is atmospheric plasma? And I like to tell people very simply, it is an ionization of a gas. So many of the products we'll talk about today can simply operate on compressed air. Our flame plasma systems will use natural gas or propane as well, but we're ionizing those gases involved, and in many cases for those that are driven off of compressed air, we're going to be ionizing the oxygen in that air. So let's talk a little bit about the different systems involved, the different technologies involved. There are 3 or 4 different technologies that relate to plasma treating as it pertains to objects, rigid 3-dimensional objects. And what we're doing is we're bombarding the surface with this ionized gas, oxygen in case of a compressed air. And there are 3 or 4 different ways that you can do this. The first would be a blown ion plasma, and in that technology, what we're doing is we're creating a high voltage electrical discharge inside the head of the system. And what you see on the picture on the left here is the resulting ionized air being blown out of that. It is a very effective technology in treating areas, tend to be smaller areas and at fast speeds. A blown arc style plasma is probably most similar, if any of you are familiar with corona treatment for flexible films, it's probably the most similar to that. Here we're taking a high voltage electrical discharge and blowing that in a wide fashion, anywhere between 2.5 and 3.5 inches wide. Great for large areas and a very flexible technology as well. The final technology I want to share with you a little bit today is what we call flame plasma. And as I mentioned earlier, flame plasma technologies are going to use either natural gas or propane mixed in specific ratios with compressed air to create a highly effective, highly efficient, and very versatile technology. Flame treatment systems can range from very small widths to we've manufactured flames well in excess of 1 meter wide at times as well. So now that we know a little bit about the technologies, what are we doing? So we tell folks, generally you are going to clean, etch, and functionalize the surface. And you'll see a very similar graphic here, except this one's a little bit happier. So after plasma treating, you're going to have a high energy or a higher surface free energy value on the plastic that you're looking to treat. What you've done is you've eliminated that surface contamination in many cases. That's the clean part. You've also knocked down any migrating additives from the surface. That does not mean that there are not additives still in your plastic, so you do want to make sure that you're treating immediately prior to whatever process you're going through, because those additives can then bloom up to the surface again. And the etching and functionalizing component has added increased bonding sites. When we say etching the surface, this isn't something that you should be able to see with the naked eye. If you pass your part through one of our systems, if you're doing it right, it should look exactly the same to you both before and after plasma treatment. If you look at that microscopically, you are going to see a rougher surface with increased bonding sites. All of these things lead to a hydrophilic surface and one that wants to promote strong adhesion. So this is a good image to kind of give you an idea what happens before and after treatment. So the image here indicates an ink, adhesive, or coating, a droplet of that on a surface that has not been treated. What you see is it kind of beads up and stays in a droplet form for the most part. I like to give the example to folks, if you think about washing and waxing your car, inevitably the next thing that happens is you park outside and it rains. And at that point, the water is going to beat up and roll off. And that's the same effect that you get in trying to put down an ink, an adhesive, a coating, a paint on a surface, on a plastic surface in particular, that has not been treated. After treatment, it's more like, you know, a month or two after you've waxed your car and that rain kind of sits on your car itself. It's going to lay down a little bit more flat, and that's what we're looking for to get a good, strong bond on your product. One of the tests that we've run with a UV cured adhesive was on a polyethylene substrate, and we measured these values 24 hours after they were treated, the adhesive was applied and cured. We had a control sample which was not treated, that same adhesive was applied. We then tested also with our blown ion technology as well as our flame plasma technology, and what we found is that pre-treatment with both blown ion and flame yielded an increase in bond strength by a factor of 3.5 times, so pretty significant. So let's talk a little bit about what steps you need to take in selecting and integrating plasma treatment into your line. So as you talk with one of our application experts, we're going to ask a few questions. I talked about material on the front end. That's a very important part to know. It helps us zero in on the technology that might be right for your application. And that's one of the benefits at Enercon that we have, is that we do have a full complement of the plasma treating systems that are available, blown ion, blown arc, flame, as we talked about, as well as those technologies which you can add a process gas to on more difficult to treat applications. We're going to want to know if the part is conductive or non-conductive. Is it metal? Does it have any metal in it, or is it purely plastic? That is a determining factor on one of the technologies. We want to have a good idea of what you're going to treat on the part. Is it a small area? Do you want 360-degree coverage? What does the part look like? What's the geometry of it? So anytime you can share pictures or drawings of that, as well as physical samples, that is very valuable. We'll want to talk how the part is handled, and we'll dive into these specific ways in a couple of minutes here. Want to have an idea how fast you're looking to run, and ultimately what's the volume that you're going to be putting through. We can test all of these things for you. We have a full service lab in our facility. We do free product testing to introduce folks to the plasma treating technology. So I started to touch on how these systems could be integrated. They can be integrated over a conveyor. If you've got a part moving down a conveyor line and you're needing to treat a part, or maybe you're extruding, wire and cable, we can put them along those lines. They can be done offline too. They can be designed with a specific system where a part is put into place, indexed underneath the treatment head. The treatment head can stay stationary. You can move the part. You can move the head and leave the part stationary. There are really a countless number of ways that you can integrate these systems, whether manually, robotically, semi-automatically. We can work with you and have had experience integrating them in all these different ways. So now I'd like to turn it back over to Mike and talk about the ways and the benefits of incorporating UV into your curing process.
Great. Thanks very much, Ryan. And I think one of the things we'll touch on as well is as Ryan talked about, the importance of really understanding what you are trying to accomplish in your application, in your process, really helps to put that into effect with the technology. And we like to do the same here, where we understand what you need to do, the applications, the adhesives, inks, or coatings that you're working with, and really make sure that it works for your process. And so I think it's a really nice fit. As we look at LED, it's going to change. And so as we look at some of the benefits of UV curing, we have lots of people who are already doing UV curing, enjoying some of the benefits of UV curing. The idea that it's typically an instant cure, it's a cure on demand. People are already looking at it as a cost savings versus some of the alternative curing processes such as a thermal cure. And so a lot of these things that people have already started looking at UV curing in general, if we go to the next slide, we see LED curing takes these even one step further, and some of the benefits, the additional benefits you get from LED curing is things like low temperature curing. So for people, I think we talked earlier about doing plastics, you want to keep the temperature low so that you're not deforming the plastics. LEDs have some real advantages here. One of the real areas that people are looking to take advantage of with LEDs is with the lower running costs. Certainly, you'll use less electricity. The lifetimes of the LEDs is significantly longer than the traditional lamps. And so this is one of the areas that people are really trying to take advantage of with the LEDs. And certainly, in order to get to using an LED system, it needs to be easy to integrate. And so the systems will include things like PLC control or external control so that you can automate it. And one of the benefits we'll talk about with the LED systems is actually their environmental friendliness. And if we go on to the next slide, you'll see that this is another one of the areas that certainly LED has the advantage over the typical mercury lamps. UV curing in general is considered a green technology, but mostly because of the materials being used. And so when you have your solvent-based inks or coatings, there's a lot of VOC content. When you move to a UV curing process, you really eliminate that VOC content and move the materials now an all solids material. And so it is considered a bit of a green technology, and LED takes it a step further because now you're eliminating the mercury of the mercury lamps. You're no longer generating ozone. The mercury lamps, they produce light below 250 nanometers, which can produce ozone as it goes through the quartz of the lamp. You don't see that with LED. The less power, again, is nice environmentally friendly, and there's no consumable items, things like replacement lamps. You don't see that with LEDs. But if we go to the next slide, you'll see really one of the big things that's driving the transition from the lamp to the LED is the cost savings that people are looking for. And these cost savings can be seen in a number of different. One of the potentials here is on the electricity savings, and this is really going to depend on the size of systems, the number of systems, the power of the systems being used is going to determine the cost savings. One of the things we have on our website is the actual online calculator. You can use that and plug in some of the factors that you have in your application, how many systems you're using, the type of system that's being used, and you can actually come up with an estimate on the savings that you'll be able to achieve by switching to an LED. The example I have here to the right is really somewhat of an extreme example, but you can see in this case they were using 6 10-inch 600 watt per inch lamps. We were able to replace each of those 6 kilowatt lamps with an LED system, and you can see the electricity savings alone is so significant it actually pays off the cost of the equipment in less than a year's time. So this is really obviously one of the driving factors that people are looking for in moving to LED. Another area certainly that they will see cost savings is on the next slide here. And one of the areas that LED certainly has an advantage is with the longer lifetime. And this is one of the areas where LEDs have an advantage, but I think what we also see is that there may be some misconception with the capabilities of LEDs. And you'll see this chart shows a number of different curves. And when we look at LED lifetime, certainly the expectation of LEDs is 20,000 hours more. Some of the newer systems we have, you're looking at 40,000 hours plus. So there's a real benefit to moving to it, that the LED certainly is almost never needs replacing in a lot of applications because the on hours are all that's being counted. And in a number of applications, if it's not on 24/7, you'll potentially never get to that 20,000 hours. But one of the things I do like to point out is that the degradation of the LED will depend upon how it's being used. A lot of people don't consider the degradation of the LED. They think the LED may stay at a certain output for the length of that lifetime. But one of the largest factors that will control the degradation is the temperature of the LED. And so that temperature of the LED needs to be managed carefully within a system. And one of the areas that will determine the temperature of the LED is how much the LED is being driven, how hard it's being driven. So the chart here shows three different examples. The red curve shows an example where the LED is being driven at 100%. And you can see while it starts at 100% at 0 hours, by the time you get to 5,000 hours, you could be at a point where you've lost 30% of the output. By the time you're at 50,000 hours, or sorry, 20,000 hours, you're 50% or below of the initial output of the LED. So that could be a fairly significant change to the process. What we recommend with any system, and even with the LEDs, is that if you start your process in a fashion such as the green curve, where you're starting at about 75% of the total output of the LED to start your process, you can see now it's a much more gradual degradation. As you get out to 20,000 hours, it's lost about 20% of the output, but you now have the ability to adjust for that. So as the LED output degrades, you can actually adjust the output on your system and maintain a very repeatable process. And so as we talk about the degradation of the LED, one of the things that becomes important is the radiometry. And so as we go to the next slide, you'll see radiometry is one of the areas where people don't always take that into consideration with LED, but we think it's a very important area. Obviously, for any repeatable process, you need to be able to measure the output in order to maintain it. And although the LEDs do degrade much more slowly than lamps, they still degrade enough that it is important that you're being able to measure the output to maintain a repeatable process. Now, the LED radiometry technology is much newer than the radiometry that's being used in lamps. And so there are some challenges with the radiometry. And some of the things like narrowband spectral distribution. So most of the radiometers have been developed for broad spectrums of the lamps, and now when you're trying to measure a very narrow spectrum of the LED, there can be some challenges there. The other thing that we'll talk about a little bit more as we go is a lot of times with the LEDs, they're using lenses to focus the light, and the radiometers are not always set up to manage that. So while there are new radiometers that are being released into the market specifically for LED curing, and that's helping to overcome the challenges. And so one of the things we definitely suggest is that if you're currently using a radiometer that has been designed for a lamp-based system, that's not going to give you an ideal measurement for an LED. There's enough differences that we always suggest people to get themselves a radiometer that's designed specifically for measuring LED output. So that talks really about a bit about the technology benefits of LED, but one of the things we need to really talk about is how the LED works in your curing process. And for that, we look at the light curing factors. And on the next slide, we'll see really the three areas that the curing system can control in the curing process. You can control the irradiance of the irradiance output of the system, the length of the exposure, and the spectral content, or the wavelength of light that go to your material being cured. And it's very important to be able to control these because I like to relate curing somewhat to cooking, in the sense that what we have found is that if you take the same adhesive or coating and cure it in different ways, you can end up with a very different result. Much the same as cooking. If you take the same ingredients and you cook them in different ways, you can end up with very different results. So it's very important to set these factors and then be able to maintain them. And so if we go to the next slide, certainly one of the most important areas for curing is the power or the irradiance level. And so in order to get a UV curing process started, you need to have sufficient irradiance, sufficient energy to your material to start the curing process. And this was a concern, I would say, early on in LEDs, but today LED technology has improved so significantly that now one of the areas that people often don't take into account is that there can be excess irradiance or excess power coming from an LED system. I mentioned you have systems that are 8 12, 16 watts per square centimeter. And so that's a very significant amount of energy. It's a very high irradiance level, and a lot of the materials aren't able to deal with such a high irradiance. And so while you certainly need to have a minimum irradiance to start the cure, it's also important that you monitor that you're not giving excess irradiance to your curing, because you can overcure and have some detrimental effects on the material properties with excess irradiance. So you do need to be able to maintain that window of operation and find that safe irradiance curing level. When you talk about irradiance, if we go to the next slide, with LEDs, one of the areas that you really need to keep in mind is your working distance. So more so than lamps, the irradiance level drops very significantly with LED systems over your working distance. So the chart to the right gives you an example of how the working distance can affect the irradiance. And if we look at the numbers in the table there, you can see that at 1 millimeter, where a system may have 9 watts per square centimeter irradiance, when you go to 30 millimeters, which is a fairly typical curing distance, that irradiance level has dropped by 1/3. So it's very important to understand that the irradiance level that you're measuring right at the window of the LED system, or at 0 millimeters, doesn't really represent your adhesive or your ink is seeing at the cure site. Now, one of the areas we like to use to improve upon that is using some optics or some lenses to focus the light. And so in order to do that, you really need to understand the irradiance level that you are requiring and also your working distance. A really good example, if we move to the next slide, you can see the benefits you get from using some custom optics. And this chart here shows a typical LED system, one with the lens. The green curve here shows you the LED system with the lens. The blue is without the lens. And so you can see, while at 1 millimeter working distance, they're both fairly similar in 9 watts per square centimeter or 8 watts per square centimeter. By the time, again, you move out to about 20 millimeters, with the lens, you've still dropped, even with the lens, you've still dropped to about 50% of your irradiance. But with no lens, you've dropped all the way down to 1.5 watts per square centimeter. So it's a significant drop. It's 1/3 the irradiance that you would get with the lens. So this is really important when you're looking at what your process, what your material actually requires from an irradiance level. And just sort of to give an example, if, for example, you've determined that for your process you do need 4.5 watts per square centimeter irradiance at a 20 millimeter working distance, a lens or an LED system with the lens, you're able to use a system that starts with 9 watts per square centimeter. If you would use a system without a lens, in order to achieve that 4.5 watts per square centimeter at that working distance, you'd actually need to start out with about 20 watts per square centimeter. And so now you're talking much more LEDs, much higher output, higher electricity. And so what the lenses do, it actually makes it a much more efficient system by being able to much more effectively transmit the light from the LED down to the surface where you actually need the irradiance for your process. So that's the irradiance. If we go to the next slide, we want to look at the spectral content. And you can see from this slide, the spectral content between a lamp and an LED is very different. The blue curve there shows the typical spectral output of a mercury lamp. This will obviously change depending upon the specific lamp you're using. Some lamps can be doped with different materials to change the spectrum. This is a typical mercury lamp that we use here on our systems. And down at the bottom you can see that there's a fairly broad distribution. You have a nice chunk of energy in UVA and in UVB as well. There's a nice peak at 440 nanometers. But you also have energy in the UVB and the UVC areas. If you look at the 3 curves down in the middle, the red, the green, and the purple curve, those are examples of LEDs. And that's 365, 385, and 405 nanometers LEDs. And if you look at the content of those, you see it's very different. The 365 nanometer LED, all you have is UVA energy. There's really no energy outside of that. And so when you're looking at specifying an irradiance of, for example, 5 watts per square centimeter. If you look at the lamp, that 5 watts per square centimeter is a distribution of UVB, UVA, UVB, and UVC, versus in an LED where it's very specifically all in either UVA or, in the case of a 400 nanometer, all in UVB. So it's a very different distribution of the energy. And why is that important? Well, if we move on to the next slide, what we see is that when you're trying to match the output of your light source, you need to be able to match that to the photoinitiator of your material, whether that's an adhesive or an ink or coating. And you need sufficient energy of the correct wavelength in order to start the curing process. When you're using a lamp-based system, it makes it a bit easier. You have a broad spectrum of light. Chances are you're going to get energy in the absorption range of your photoinitiator. You're going to start your process. With the LEDs now, you're talking a very narrow range of wavelengths that you're using. And so it is very important that you match that with the requirements of your photoinitiator. If those two don't match, it doesn't matter how high in irradiance you use, you're not going to get any cure. And so for that reason, we make sure we offer a variety of wavelengths. 365, 85, 395, and 405 are all available to ensure that there is a wavelength that's going to match the requirements of your material in order for it to cure. So that's one of the challenges. If we go to the next slide, you'll see one of the real benefits of that narrow spectrum, and that's with the lower heat. And so with the narrow spectrum of the LED, you can now really match very specifically the requirements of your adhesive or your ink to what's coming out of your LED, and you end up with a very good absorption. With the lamp, what happens is you have some wavelengths outside of what's required by the adhesive. Some of those wavelengths can be absorbed by the materials that you're curing. Some of that can be absorbed by other materials within the adhesive, and you can actually generate heat in that process. The curing process is an exothermic process anyway. There's going to be some heat generated, but LEDs allows you to really specifically target the wavelengths that you require and minimize that heat. And the chart on the right really gives you a great example of where lamp-based systems, there's different ways of reducing the wavelengths using things like filters to reduce the heat, but LED has a very significant advantage. So if reduced temperature is important in your curing process, LEDs can have a real significant advantage for you. So if we look at the different wavelengths that are available, but which one should you choose? And so, some rules of thumb when you're looking at the LEDs, if we go on to the next slide, a lot of formulations will specify a 365 nanometer requirement. This has some historical precedence from the mercury lamps that have a very large peak at 365 nanometers. But what we've seen is a lot of the materials, certainly the free radicals, will cure up to and above 400 nanometers. Cationic materials do tend to cut off at about 380 nanometers, so this can certainly limit what your LED wavelengths you're able to use to cure your material. The longer the wavelength, the 400 nanometers tends to give you a better true cure, while the lower wavelengths tend to improve surface cure. And certainly one of the things to look at is we certainly see that the wavelengths 395 nanometers, 400 nanometers tend to have significantly higher power than 365. So often there can be a bit of a trade-off as to using the increased power or increased irradiance that's available from a 395 or 400 nanometer LED versus there may be a little bit of reduced absorption by your LED. So you can often have options of different wavelengths that can be used. And a great example of that is on the next slide, where not only is it the adhesive that you need to consider in your process, but it's also the substrates that are being cured. And so the example here shows where the parts being bonded together, the parts being cured together, actually had a significant absorption at 365 nanometers, and that's what that curve to the right there. If you look at the blue line, you can see that at 365, about half the light at 365 nanometer is being absorbed by the material, and it's not even getting to the adhesive. So in this case, we actually tried using a 395 nanometer LED. You can see from the green line on the curve, now you're starting to get about 80% transmission through the material. And so you're getting significantly more energy that's not being absorbed by the material. It's going to the adhesive and being cured. And so in this case, even though the adhesive had specified 365 nanometers, testing showed that the better solution was actually a 395 nanometer LED because you were actually getting more energy to the adhesive. You were getting less heating of your parts. This is just an example of some of the things that we can actually do for you as well. We have a material testing lab on our site. And so we can test the transmission of your parts. We can test the ability of the different wavelengths to cure and make some suggestions on which wavelengths may be more suited for you. Again, this is one of the areas that becomes more critical with LED because of the narrow bandwidth of light. With lamps, this was an area often overlooked because with the broad spectrum, even though some of the wavelengths may have been absorbed by the material, if you're getting enough energy through to the adhesive, you'll get curing and may not realize that your material is actually absorbing a significant amount of the energy. The last thing I want to talk about as we go to the next slide is the surface finish. And this is an area we see quite frequently with free radical materials. And I talked about the emergence of this LED technology in medical, and this is one of the areas we see certainly in medical device where free radical adhesives are used quite extensively. And what we see sometimes with free radical adhesives is something called oxygen inhibition, where although the adhesive may be cured, it ends up with a tacky surface. And that's because the oxygen prevents the full cure of the adhesive right on the very surface. So there are different ways that you can minimize the oxygen inhibition and improve surface finish. And one of the common ways of doing that was using UVC energy, and you can see the little blue area in the spectral chart to the right there shows you the UVC area, or even UVB, where customers would often use short wavelengths to improve the surface cure. Unfortunately, with LED, what is commercially available today, really the lowest wavelengths we go to is 365. So it doesn't really give you the benefit of that UVC, UVB energy to promote a better surface cure. So in this case, there are different ways of improving the surface. You can use things like a nitrogen purge. Sometimes even a higher picoradiance might help. But it's one of the areas just to keep in mind. With the LED, you don't have that benefit of the UVC energy. With that, we'll go to the next slide, and I do want to quickly give you just an example of one of the advancements we have seen, or we have come out with our UV curing technologies. And this is our OmniCure AC2 UV LED systems. And I like to talk about this one because this is a great example of an LED system that can be used across many different applications. We've seen this used in areas like printing, 3D printing, in medical devices, and even electronics applications. It's a very compact system with a quite impressive output of over 4 watts per square centimeter for a very compact size. It comes either 3 or 4 inches wide. But the technology built into this system allows you to actually join up systems. So you could actually cure areas as wide as you want because the LEDs go right to the end of the system. And that allows you to join the systems. And the technology built in allows you to join those systems without any significant loss in the uniformity between them. And so there is patented technology in our systems that allows us to control the LED modules within each system that allows us to achieve very high uniformity. These are all air-cooled, gives you well over 20,000 hours of lifetime. And again, we see these being able to be used in things like medical, electronics, and printing applications. With that, I'm going to pass it back to Ryan, and he'll talk about some advancements in the plasma systems.
Thanks, Mike. Some of the things that we've been working on at Enercon has really been looking at how do we take our proven designs, our proven technology in both our blown ion and blown arc series plasma systems and add some additional technology which will greatly enhance the effectiveness of the system and what the user experience is online. So we've gone through and added a very intuitive touchscreen system. This is a system that we've developed internally. We actually run it across 2 other products as well that Enercon manufactures. And we've had the ability to learn what users want to experience on the system and what features they want to use. One of the great features that this adds is you're able to buy either a blown ion or blown arc system with a single head or 2 heads on them. And with that design, we are now able to offer really truly independent head control. You can start and stop one head at a time. You can link them together, start and stop them the same. As well as we've integrated what we call plasma integrity monitoring. We're monitoring all the critical aspects of the system and how it's running to ensure that you have a repeatable process, and that's something that you can monitor either on the system, or our Pro-style systems do have built-in Ethernet capability, which will allow you to integrate that into any control system that you would like.
All right, thanks Ryan and thanks Mike. Let's just do a quick summary of some of the things we've learned today before we go to the question session of the program. Plasma and flame surface treatment is designed to clean, etch, and functionalize surfaces to enable UV curable coatings to bond with the surfaces. Defining your application is key to knowing which surface treatment technology will be best for your application. The best place to integrate plasma or a flame treater is directly prior to applying the UV curable ink, coating, or adhesive. New LED products are now available with higher output and a smaller footprint. LED systems benefits include lower cost of operation and lower heat. And the curing challenges can include adhesive compatibility and surface cure, and testing is truly the only way to confirm compatibility. With that, we're going to switch over to the question part of our program. And Ryan, the first question is, are plasma surface treaters and flame surface treaters usable not only on plastics but other materials, glass, metals, etc.?
It's a great question, and one that we get daily, Mark. Plasma treating systems, whether blown ion, blown arc, flame plasma, variable chemistry plasma systems, can be used on a wide variety of materials. There are some limitations when it comes to that, really in the fact that a blown arc technology cannot be used on a conductive or metal surface, but for example, our flame plasma system is often used in treating metal objects, and most often treating might be a little maybe a little misleading, in that what we're really doing on metal surface oftentimes is cleaning some sort of substance off of the surface that was used in manufacturing, oftentimes an oil that might be used in the manufacturing process of that metal.
Thanks, Ryan. Here's another question. How does the functionality created by plasma treatment change over time?
So plasma treatment, one of the things that you want to make sure that you look for is that you are integrating that plasma treating process immediately prior to whatever you're doing. If you're curing an adhesive, you really want to put that plasma treater in line right before that process. Same thing with the coating or printing application. And the reason behind that is the plasma treatment will degrade over time. Now that amount of time varies by application to application, and this really goes into one of the first pieces that we discussed this morning, in that what you're looking at is different plastics involved, different additives involved, and all of those things combine to make a treatment that is not always predictable on how long it will last.
Thanks, Ryan. Here's a question for Mike. Mike, how can someone know if LEDs can be used with their current adhesive?
Oh, thanks, Mark. That's a good question, one we get all the time as people are using the lamp technology. They don't like to switch adhesives in their process, and so want to know whether LEDs can work. And really the only way to know for sure is testing. We have seen there are a significant number of LEDs, or adhesives, sorry, where the LEDs are quite compatible and will cure. But that doesn't always mean that the properties of the final cured adhesive are going to be the same with the LED as they are in their current curing process with the lamp. So they really need to be able to test that. Again, this is one of the areas we are often able to help customers by doing some testing in our own labs. We can test the compatibility of the different wavelengths. Again, the composition of the light is very different on an LED versus a lamp. So it really is a question mark where testing is the only way to know for sure. A lot of times, yes, but there could be things such as the substrate being used may not lend itself as well to an LED. So testing is the only way to know. I would say in general there's quite a significant number of adhesives available that work very well with LED. Over the last few years, we've seen a very significant increase in the number of inks that have been specifically formulated for use with LED. And one of the areas we're really seeing some emerging growth as well is in the number of coatings now that are being formulated for specific use with LED. And that's just with the increased adoption of the LED technology. We're now seeing that also that growth in the number of formulations that are available to work together. So hopefully that answers the question.
All right, thanks, Mike. This is another question. When using a flood UV curing box, how would the watts per centimeter square degradation curve look, degradation versus distance?
Okay, so on a flood system, again, it's going to depend upon potentially the specific optic or lens that's being used. But the degradation curves that I had shown with and without optics is a great example of how that will look on a flood system. That was actually, that chart there showed an example of how the irradiance level degraded over the working distance with a flood. And so one of the things with LEDs is the light coming from an LED is quite divergent. And so that's why we see a very significant drop in the irradiance level. And so I think what we showed on the chart is that, you know, without a lens, over 20 millimeters, you're dropping to about 1/3 the irradiance level. Versus with a lens, you can really improve that and have a very significant advantage. So I think the chart I showed is a great example of showing how the degradation does really affect the irradiance level as you increase the working distance.
Thank you, Mike. Ryan, here's a question. Once a substrate is plasma treated and there is bonding to an adhesive or coating, is it reversible, or could the bond lose its strength over time with aging?
Once you have plasma treated an object and then bonded something to it, that bond typically, I don't know of a case where this isn't true, but that the strength of that bond will stay the same. That the results of the degradation of the plasma on an untreated surface is not related to that of one which has been bonded to. So once you make that bond, we'll see that level of bond strength stay the same throughout the life.
Mike, how do you relate dosage using a lamp versus using LED?
So the dosage is measured in the same way. The dosage is the irradiance and the time. The big difference, though, again, is it going to be in the content of that light. So the irradiance level from a lamp is including wavelengths of light from both UV, or from UVB, UVA, UVB, and UVC, versus the LED, which is strictly really in the one band, depending on the LED being used. But the actual measurement of dosage is still the same. Again, we always recommend that you use a radiometer specific to measuring an LED. And these radiometers are available that will give you specific dosage readings in joules that tell you the irradiance and the time that you're getting, and so that you can use that information in your curing process. Obviously, a lot of the materials are going to require a specific dose of energy for curing, and so you can measure and relate that. Again, the question becomes whether or not the dose being specifically in just one band of wavelength is going to give you the same curing as a dose with a lamp that gives you a very broad spectrum of light. And that's why we really need to test.
Thanks, Mike. Looks like we're coming up at our 1 hour of the presentation. We've got time for a few more questions. Ryan, is contact angle a valid surface energy measurement with a plasma-treated surface? What about dyne level?
That's a great question, and thanks for bringing that up, Curtis. That's one that we didn't necessarily talk a lot about in this presentation, and may have touched on it, but didn't dive into it. So there are really, 3 or 4 ways that you can measure the effects of plasma treatment on the surface. The quick, cheap, and easy way is to do a dyne test. It is a very easy test to conduct. Folks many times either have dyne solution or dyne pens in their facility, and it is usually a easy test to conduct. It is a bit subjective in that the person conducting it may read a dyne level one way, someone else may read it another, but you're going to get a pretty good feel for where that's at. Contact angle is indeed another. You're adding a piece of equipment into the fold, but another good way to do that. The other area that you can also look at using is ultimately measuring both the polar and nonpolar groups on the surface for the surface free energy. And that's again probably another advanced way to do it, but it allows you really to look at diving into levels of understanding not only what the polar nonpolar groups are at the surface of the material that you're trying to bond to, but then understand what those groups are in the material you're bonding as well, and that can play an advantage. The true test, however, is really, do you get good adhesion on your product of what you're trying to bond to? That is, that's the key. We can have dyne levels that show us one thing, and the bonding happens to show us another thing. So that's where you tend to, dyne level sometimes will give you a false reading at sometimes as well.
Thanks, Ryan. We'll take one more question here. Mike, this one's for you. Are LED-based curing adhesives used commonly in the field of medical devices? If then, what are some of the uses, and what is the FDA stance on LED using adhesives?
Okay, so there are a number of new adhesives that have come out that are specifically targeted for LED curing, and these adhesives do have the medical approval. So they have the ISO approvals for use in medical devices, and so in that sense, they are approved for use as current lamp-based adhesives would be. Obviously, from an FDA point of view, you need to go through the testing process with the LED. Any testing, any information or data that you have from testing with a lamp system would no longer be valid for the work you have with the LED system. But there are definitely, some of the major suppliers of adhesives for medical device, medically approved adhesives, have come out with some that are specifically targeted for LED, and they would have the same approvals as the existing ones. But it does mean going through the testing and the process once again, and that's what we've seen over the years has been one of the challenges and one of the reasons that the medical device manufacturers have been slower to make the adoption to LED. But it's one of the areas we do see now as emerging, is that they're going through this process. They're taking one of the adhesives that are available and going through the process to get it approved. So they are available, and they would meet with the same approvals as the current adhesives.
All right, I'd like to thank Mike once again, as well as Ryan, and our audience today for attending. Again, this webinar was recorded. It will be made available to you along with presentation slides within 24 hours. Again, we appreciate your interest in today's topic. If we didn't have time to get to your question, these gentlemen will reach out to you and make sure that your questions are answered. This will conclude the webinar, and we hope to see you at a future one.